signed in here. Actually, okay, never. Okay, last time we looked in section 2.5 at the chain rule, that if we've got a composition, the derivative of the composition, we take the derivative of the outer function, still at what's inside, times the derivative of the inner function. So, and I think, I'm not sure I got to what question 1 addresses. So let's just go through question 1. We had talked about continuous a few sections ago. So the idea of continuous is no breaks or jumps or gaps. Whereas the idea of differentiable is the tangent line exists. Well, if there is any kind of break, or jump, or gap, we can't talk about a tangent line to the curve there. So, in this particular case, at -1 the function's not continuous. It makes no sense to talk about the tangent line there, because there's no point there. Similarly at 4, it makes no sense to talk about a tangent line to the curve, because the curve's already doing something weird. So, there's a very real sense we have to have continuity before we can talk about differentiability. But differentiability, we still need a definitive slope of the tangent line. And so the things we've got to watch here, in addition to none of these, we need to make sure there are no corners and no vertical tangents. So here we've got a corner at 1. We're heading in one direction and then abruptly change to a different direction. So what direction are we headed right at 1? Well, we don't know, because from one direction we're going, from one side we're headed downward fairly rapidly. Put this on. So from one side it looks like that's the slope of the tangent line, or that would be the tangent line, but on the other side it writes an abrupt change. The function's not differentiable there. Similarly at 2, there's a corner. So as we look at places where the function's continuous, we don't want any of these problems. So in 1, this function's continuous at 0, not at -1, but at 0 it is, at 1 it is. Something weird is happening at 1, but it's not a problem with continuity. There's no jump or gap. It's continuous at 2, at 3, not at 4, but at 5. So in terms of where it is continuous, this is at x equals, what did I say again, 0, 1, 2, 3, and 5. The only problems with continuity here are at -1 where there's a hole, and 4 where there's a jump. Whereas for differentiability, it first has to be continuous, so there's no point in even thinking about -1. The function's not even continuous there. So at 0, is the derivative defined? Yes, it is. But at 1, it's not. Because the slope of the tangent line, there's not just one value for that slope. So this function's differentiable at x equals 0. It's not differentiable at 1. It's not differentiable at 2, because there's a corner. It's fine at 3, and it's fine at 5. Corners can come up, especially when we start doing compositions involving the absolute value. The absolute value has a pretty pronounced effect on graphs. I mean, in fact, if we compare the graph of x, y equals x, till y equals the absolute value of x. Where x is positive, they're exactly the same, but where x is negative, it flips it up. And so because of the change in definition where we go through 0, there's an abrupt change in direction. And so the absolute value is going to do that a lot. And so when we see some functions where we're headed in one direction, all of a sudden we head in another, probably that's an absolute value function involved. For our purposes, we just need to realize it makes no sense to talk about the derivative right there, or there, or any place where it's not continuous. Okay. Other questions from the homework in 2.5? 11, okay. I mean, I skipped a few of these because doing it from the table is something I didn't really want to worry about trying to do. So 11, we've got our function f of x is the square root of x squared plus 6x minus 1. So it is a composition. We've got something other than just the square root of x. For the derivative, it's probably better to recognize this as x squared plus 6x minus 1 to the 1/2 power. So our outer function is we're taking something to the 1/2 power. So in terms of the derivative of something to the 1/2 power is 1/2. That's something to the 1/2 minus 1. We apply the power rule. The argument stays the same, but then in the chain rule we take the derivative of that argument. So we do take the derivative of f and the derivative of g, it's just we end up with a product. The derivative of f still evaluated at the same inner function it was before, then times the derivative of what's inside. In fact, that's another form I gave for the chain rule, that the derivative of the outer function still at the inner function times the derivative of the inner function. So let's see, we've got 1/2 times x squared plus 6x minus 1 to the minus 1/2 power, and then times 2x plus 6, taking the derivative term by term by term. The derivative of a constant is always 0. This will simplify a little bit. 2x plus 6 has a common factor of 2, which cancels with the 1/2 out in front. And also, lots of times we don't like the negative power, so we could put this in another form saying, well, this is over x squared plus 6x minus 1 to the 1/2 power. And we might go ahead and put it back in terms of the square root. If all we're looking is finding the derivative, and there will be on the upcoming exam a number of questions where it's find the derivative. Once we have taken all the derivatives there are to take, we can stop. You don't have to worry about would this simplify, can I simplify, what simplified form does Dr. Hopkins want? As long as you've got the derivative, that would be the point of that problem. If we're going to do something with the derivative, evaluate it at a value, although evaluated at a value, we still probably wouldn't have to simplify with all the variables in there. Just put in, say, x equals 2 if we wanted to know what's the derivative at x equals 2. But certainly if we were looking to, say, solve where this is equal to 0, then we would want to simplify it some in that process. So it depends a little bit on how much simplification we want to try to do with these problems. If the problem is just what is the derivative, once we find the derivative, that's fine. We can leave it that way. Okay, other questions?
Number 9.
Number 9? So 9, we've got f of x is x times 3x plus 7 to the fifth. And we're asked to find the derivative. Here, if we look at it, the last thing we do is we actually multiply two pieces. So in terms of the derivative, the first thing we need to do is apply the product rule. Which means we have to remember the product rule. The derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. So for this particular one, it's the derivative of the x times the second plus the first times the derivative of the second. Derivative of x we've done a few times, that's just 1. Derivative of any linear is the slope of the linear. So 1 times 3x plus 7 to the fifth plus x times. For that derivative, that is a composition. We're going to have to use the chain rule. We've got something to the fifth power, so the derivative is 5 times that something to the fourth power times the derivative of what's inside. And the derivative of what's inside here, derivative of a linear, is just the slope. And so we get here 3x plus 7 to the fifth plus then 15x times 3x plus 7 to the fourth. There are a couple things we could do in attempting to simplify this. Certainly if we wanted to figure out where this was 0, realizing that there's a common factor that could be factored out would be helpful. But for just the derivative, that's fine. In fact, as we talk about finding the derivative, it's probably a reasonable time to tell you there are sites on the internet that will find the derivative for you. My favorite one on that is what's known as Wolfram Alpha, a computational knowledge engine. It will do lots of things. Depending on your level of curiosity, you could get kind of lost here comparing, say, the frequency of your name to the frequency of somebody else's name, or what's the population of this city. But for our purposes, we just want to find the derivative of x times 3x plus 7 to the fifth. And it does some working, some thinking, and it gives us an answer, and notice the answer it gives us, 3x plus 7 to the fourth times, what is that, 18x plus 7, doesn't look like what we've got here. Well, they've actually done a little bit more simplification. They actually have factored out the 3x plus 7 to the fourth. That leaves one of them here, and just the 15x there. And if we add this, we do get the 18x plus 7, and it's times the 3x plus 7 to the fourth. That's the answer they gave. So we came up with that answer, took a little bit with that. So the process of finding the derivative can actually be programmed fairly well. I mean, this is one site that will do it. It's running off a program called Mathematica. It's now in like its 10th or 11th edition. Came out originally before most of you were born, because I think it was the early 90s. It started coming out what's called a computer algebra system. But much like the dilemma, say, even in elementary school, where you teach students how to add numbers. If they're really big numbers, we will pull out a calculator to add. But there's a sense we do need to know how to add numbers, understand that process, and not just trust the calculator to always do it for us. That's the same kind of thing we have here with the derivative. Yes, it will compute the derivative, but there is some benefit to learning how to compute the derivative. And our bigger focus really is kind of on, well, what's the derivative telling us? And that's what we're going to kind of look at today, is revisit that topic of, okay, what is the derivative telling us, and how is the derivative and the function related? What does the function tell us about the derivative and vice versa? What does the derivative tell us about the function? So, other questions from this homework?
Number 7.
7? So 7, we've got the function is 2x minus 8 to the 5th power, and we want to find the derivative. So we've got something to the 5th power. The derivative of something to the 5th power is 5 times that something to the 4th power, and then times the derivative of what's inside. That derivative is 2. Derivative of linear is just the slope. And so we get here 10 times 2x minus 8 to the 4th power is our derivative. So as we think about derivatives, we've got the power rule that continues to show up. We've got the product rule that may continue to show up. The quotient rule, we've added the chain rule. And so we've got a number of rules, and that's one reason on the upcoming exam, April 10th, you can have a formula sheet. And I want you to know how to use the rules, not to put your time into trying to memorize all those rules. But focus on, okay, how can I use those rules? So as you work through these problems and find yourself flipping back in the book, how exactly do I do that derivative? Well, that's probably a good thing to get on your formula sheet. Okay. I think have we done them all? I guess we didn't do 13. Actually, let's talk about 13 as well, because that does relate to kind of where we're headed today, and I think makes a good segue into where we're headed today on 13. We're asked, how are the graphs of f of x and f of x plus k related? So if we think about it, we actually have done this problem before. I mean, adding outside the function just shifts everything vertically k units. So this is just a vertical shift. So if we had some idea of what the graph of f looked like, so if f looks something like this, f plus k is just going to move everything up k units. But it's going to look exactly the same. Or down k units if k is negative. But adding k just shifts the graph. In terms of the derivative, let's look at the derivative of f of x plus k first. Derivative of a sum is the sum of the derivatives. So we can take the derivative of f plus the derivative of k. And what's the derivative of a constant? It's 0. So we just get the derivative of f of x, which is what we get if we just take the derivative of f of x. So in fact, these two have the exact same derivative. And the reason that's important for us is the derivative is telling us something about the shape of the curve. These two curves have the same shape. One has just been shifted from the other. So in terms of the derivative, the fact that the derivative turns out to be the same shouldn't be surprising when we begin to think about what the derivative is telling us. If the derivative really is giving us information about the shape of the curve, those two curves have exactly the same shape. They are both increasing over the same x intervals. Moving it up doesn't change where it increases, doesn't change where it peaks or levels out, doesn't change where it decreases. It just is shifting it. It doesn't change anything in terms of the inputs. So the fact that the derivative is the same shouldn't be surprising because the shape is the same. Okay. And with that, that's a pretty good segue into what we're going to look at today, and that's some things about optimization and curve sketching. How does the derivative help us? So, if you've got your homework ready to turn in, you can pass that up and I'll collect it. And I should highlight a couple of things here. I gave you the review sheet the last time, mentioning the page of notes you could prepare, but we've got lists of topics, some problems from the book you can do, solutions for this will become available. I think I've got them set for coming Monday, so you can work on some, but then see the solutions on Monday, and then some additional problems related to the topic. So, today's our last new material. Probably Tuesday we'll spend much of Tuesday taking questions over the problems, and then Thursday we'll have review, and then the test the next Tuesday. So, this is our last topic, and hopefully it kind of brings us back to where we started, because we started with looking at the graph and trying to figure out some things about the derivative. And we're going to reverse that. If there are some things we can figure out about the derivative, that tells us some things about the graph of the function. So, a couple concepts we kind of talked about, but perhaps not defined as well, are the local extrema, the local max and the local min. So think of it sort of as a range of mountains. We have some local maxes. Notice it's not the highest peak, but it's the highest thing nearby. We've got another local max, and we have some local minimums. Not the lowest valley, but the lowest thing nearby. So we can find some minimums. And certainly from the graph, we can identify where the max and mins are. What we're going to try to do is there something about the derivative that would help us figure out where these are, even if we don't have the graph? And the extreme value is the generic term that covers both. So in a sense, we're looking for the extreme values, both the high and low points of our function. And optimization is the process of finding those. And as you think, I mean, if you were putting together a business plan, and it sort of decided you've got this function that's going to model your profit, you'd really like to know, well, at what level do we hit a maximum profit? And at what sort of level of production do you have minimum profits? Where are those peaks and valleys? Because you'd really like to set up the business to operate at peak efficiency and really at the highest peak. But if you're not sure where those are, how do you know where to kind of put together the production level or how to operate the business that way. So we're going to be looking for the peaks and the valleys, which is called optimization, that process of finding them. Now, as we do this, a couple of things we've got to keep straight. We have the min and the max value, which is the output. So if we follow this across, this value here is the local maximum value. It's the output we get. In terms of a business, that's really sort of what we're most interested in. When do we hit the max? I mean, what is the maximum profit? But we're also interested in when does that happen? So we've got the input here, that is where the input, where the maximum value occurs. And notice they're related. And so even though the local max value, our maximum profit, may be what we're interested in finding, we kind of need to figure out at what level of production does that happen. So those two are related. Now, certainly from a graph, we should be able to spot both. So here's a graph. And we should be able to figure out from the graph what the local maximum value is. So as we look at this graph, we should be able to determine the local maximum value. So our local maximum value, the peak is at a height of 3. That is our local maximum value. The 2 is actually the answer, I think, to the next question. Where does it occur? It occurs in an input of 2, but the value is 3, and oh, nobody said minus 3. We had that for a while going on. So for this graph, where would you say the maximum value occurs? And it does occur at x equals 2. So from the graph, we can make those determinations. We can spot and see that the maximum value is the actual height. The where it occurs is the input value. And we're interested in both, but we have to be sure not to confuse the two. So there's what is the highest peak, or what is the peak, and where does the peak occur? So what about this one? What would you say is the local minimum value? And I would agree it's the minus 3. That's the lowest output we get locally. Now we are lower over here, but the way the graph is, that it would appear this graph keeps going down. And so in terms of local, the endpoints of the graph are not local. We really have to be able to see on both sides to call it a local extrema. And where would you say this local minimum value occurs? And where it occurs is at x equals 4. The input. So again, we've got the local value that we're interested in, but we also have to figure out, well, where does it occur? And on the graph, we don't necessarily have to figure out where it occurs to know what the value is. But when we start trying to reverse this, it is going to be important to identify where the value is occurring before we can find what the value actually is. there's another thing, and we've done this before, but let's just think a little bit. At 1, is our derivative here positive, negative, or 0? And remember, one of our interpretations of the derivative, it's the slope of the tangent line. So we're at 1, tangent line is something like that. That's a fairly steep positive slope. So our slope is positive, which is what most of you said. What about at 2? What would you say the slope of the tangent line is? Or the derivative? And that's our main interpretation of the derivative. It's the slope of the tangent line. And so at x equals 2, or at least fairly close to 2, it appears we have a horizontal tangent line. And so I'd say the slope is 0. Those that said negative may have been over here and thinking, in which case, yes, negative is correct. Because the peak wasn't exactly at 2, but it's pretty close to at 2. What would you say at 3? Is the derivative positive, negative, or 0? Well, at 3, tangent line looks something like that. The slope is negative. So from the graph, we can make those determinations. And in fact, this I think is kind of where we started the whole discussion about derivatives. From the graph, we can make some interpretations about the sign of the derivative, looking at it. And so I think you get the idea. At 4, the derivative is 0. Slope of the tangent line looks to be 0. At 5, we're back to positive. Now, at the x values where a local min or max occurred, was there any kind of pattern that we could spot about what the derivative was doing? Well, our local min and max were here at 2, where we had a slope of 0, and at 4, where we had a slope of 0. In both cases, the slope is 0. In general, it turns out that is not a coincidence. The local mins and max are always going to occur where the derivative is 0, or undefined, if there's a corner. If we're headed in one direction and abruptly change to a different direction, well, we might hit a peak there as well. But for the problems we're going to see, we'll talk about this idea, but computationally, we're not going to compute many derivatives where this happens. We're going to compute a lot of derivatives, though, where the derivative may be 0. And that tells us something about the function then. So we had, back in 2.2, did some sketching of the derivative from interpreting the graph of the function. And so we can do that here. Okay, let me try to do it on the board. So we have the original function. It looks something like this. And in terms of the derivative then, or the slope function, we commented here at 1 the slope was positive. By the time we get to 2, the slope is 0. At 3, the slope was negative. At 4, the slope was 0. And at 5, the slope was back to positive. So we can get some sort of graph of the derivative. And when we were doing this back in section 2.2, our big interest was, let's make sure we know where the derivative is positive and where the derivative is negative. Now, let's address this question. At values where the function is decreasing, is there a trend in what the derivative is? Is there any kind of correlation between places where the function is increasing and what the derivative is doing? Let's see, most of you said, and I would agree, it's positive. Notice we're increasing here, the derivative is positive. Where it's decreasing, the derivative is actually negative, and then when we switch back to increasing, the derivative switches back to positive. So there's a very real connection between if f is increasing, the derivative is negative, or excuse me, is positive. And if f is decreasing, the derivative is negative. And what we did in terms of our graph was, if we started with the graph by using that information, wherever the function's increasing, the derivative is positive. Where the function levels off, the derivative is 0. In fact, let me kind of put that in here as well. The derivative is 0 wherever we have local extrema. And then when the curve is decreasing, the derivative is negative. So I already answered this question. At values where the function is decreasing, the derivative is negative. So there's a connection. And also, well, actually, I haven't asked this question yet. So let's think one more thing. At the values where the local min occurs, and for this graph there's only one of those, is there a pattern in what the derivative is doing? And I give 4 potential patterns about what the derivative might be doing at, and this one's at the local minimum. So at the local minimum, here, before, our derivative is negative. It levels out so the derivative is 0, and then it switches to increasing where the derivative is positive. So at the local minimum, our derivative is negative before that value, then it's 0, and then it's positive. So B is our answer here. If it was positive before, we'd be increasing, then 0, and then negative after. that's where we'd have a local maximum. Probably just gave away the next question as to what happens when we have a local maximum. So I did. The local maximum, the function is increasing, so the derivative is positive, levels off, so the derivative is 0, and then switches to decreasing. So there's a pattern going on with the derivative that matches the pattern going on in the graph. And what we've noticed here is a couple things. Critical numbers, we're going to give a meaning to this term where the derivative is 0 or where the derivative is undefined. If it's undefined because there's a corner, we call it a cusp. But all those are critical numbers, and that's where we seem to always find our local extreme values. Our local max and mins are those places. And at our local extreme values, there's really 4 things that could happen. Or at the critical numbers, there are 4 things that could happen. We could have this scenario. The derivative is negative, so the function's decreasing. Then it's 0, so the function levels out. And then it changes to positive. The derivative is greater than 0, so the function's increasing. And if that happens, we have a local minimum there. If, on the other hand, our function has a positive derivative, so the function's increasing, then it levels off, and then the derivative goes to negative, so the function's decreasing, we'd have a local maximum value there. Notice the critical number C is where this is happening. It is not the maximum value. The maximum value, we've got to go back to the function. So when we were looking at the graph, trying to make the distinction between the highest height and where it occurred, that seemed to, we're only interested in the highest height. We weren't all that interested in where it occurred. But as we try to go the other direction, we have to figure out where it occurs first. Then we'll calculate, okay, what's the height there? And where it occurs is potentially any place we level off. That's our candidate for highest points and lowest points, is wherever we level off. And the 2 most common scenarios there, we are headed up with the positive derivative, we level off, and we go down, so then we have a local maximum. And in fact, we can and will, in just a little bit, determine from the derivative itself where exactly is the derivative positive. Where is it 0? Where is it negative? That gives us information about what the graph's going to look like. If the derivative's positive, we know we're headed up. If the derivative's 0, we know we've leveled off. If the derivative's negative, we know we're headed down. And we know we went through a local maximum then. And we can figure out exactly what the height is. There are a couple other scenarios that could happen. It is possible we could be headed up, level off, and then keep heading up. So the derivative was positive, was 0, and didn't switch signs. It stayed positive. That's not a local extrema. Or we could have been headed down. The derivative was negative. We level off, and then we keep heading down. And certainly there are scenarios, in business where it is difficult to distinguish, say, this from this, as it's happening. The economy's growing. That's good. It's starting to level off. That's a little scary because we don't know if it's going to go back, if the economy's going to go down or level off and then keep growing. For the economy, that's what we'd like. Even if the growth slows down and kind of levels off for a little bit, if we can kick it back into growth mode, that'd be great. This would not be so great. Whereas, say, if it's unemployment, unemployment's on its way down, it's leveling off, it might switch and go back up, or unemployment, we really would like to have it, after it levels off, then maybe figure out some way to keep the unemployment going down. But it's the derivative, the sign of the derivative, that's going to tell us whether our function is headed up, or headed down, or leveled off. And then we can decide, have we changed the direction we're going when we leveled off, in which case we've got a local extrema of some type. Technically, this is what's known as the first derivative test. That if we've got a function, we've identified where the critical number is, and we decrease, level off, and increase, we know there's a local minimum there. If we increase, level off, and decrease, we know there's a local maximum. If it's increasing, level off, and keeps increasing, or decreasing, levels off, and keeps decreasing, we don't have a local extrema. The leveling off is curious to know, but it's not really a point we're interested in. We are interested in figuring out where the maxes and mins are and what their value is. And where they are potentially any place the derivative is 0. That's where the function is going to level off. And we should be able to study the derivative and make that determination. So we're going to kind of try to flip things, because we've been working a lot from the graph to figure out information about the derivative. But now we're going to try to flip it. If we can get information from the derivative, that will tell us some things about the graph of the function. So we're going to analyze our derivative, try to determine where it's 0, where it's positive, where it's negative. That will tell us some things then about the function. Where is the function headed up? Where is it level off? Where is it headed down? And we can use that information to help us graph it then. So let's do this with this particular function. So we've got here, 2x cubed minus 3x squared minus 12x plus 5. First thing we want to figure out now is, well, what's the derivative? Because this is too complicated for us to just graph. So we're going to try to analyze the derivative to help us come up with the graph. So we first have to figure out the derivative. So term by term by term, the derivative 2 times 3x squared minus 3 times 2x, and then for the linear, it's just the slope, minus 12. And so we get here 6x squared minus 6x minus 12, which was b. So we've got that derivative. For our analysis, let's figure out where this derivative is 0. That's the critical numbers. So we need to try to figure out for this particular quadratic, where is this quadratic equal to 0? So we definitely have to think that. How do we solve quadratics? So in terms of solving this, I would factor, there is a common 6 I'd factor out. And hopefully that factors a little bit more. I think it does, x minus 2 and x plus 1. So either the first factor is 0, which won't ever happen, x minus 2 is 0, or x plus 1 equals 0. So either x is 2 or x is negative 1. Those are the only two candidates for where the derivative could be 0, and that's C. So that's our first step, figure out where the derivative is 0. Our next step is to figure out, okay, those are places where the derivative is 0. Those are potential peaks and valleys. So we need to decide, okay, on this first interval then, we're now solving, trying to figure out, is this expression positive or negative? And it can only switch signs where it's 0. So before negative 1, is this derivative, and any form is fine, but is the derivative positive, negative, or 0? Or does it change sign somewhere in this interval from negative infinity to negative 1? So can we figure out the sign on that interval? Well, we're back to a question I think we did section 1.5 or 1.6 where we're looking at polynomial inequalities. You may have wondered, why do we want these polynomial inequalities? Well, here's why. We're interested now in figuring out when this polynomial, when this quadratic is positive, negative, and 0. We figured out where it's 0. So from negative infinity to negative 1, since nowhere in here is it ever 0, if it's positive once, it's always positive. If it's negative once, it's always negative. So let's just test a point, say negative 2. The derivative at negative 2, we get, I'm going to use the factored form. 6 times negative 2 minus 2 times negative 2 plus 1. 6 times a negative, that's going to be positive, which tells us the function's increasing here. We now know something about the function. Before negative 1, the function's increasing, it levels off at negative 1. And then we need to figure out what happens next. So, from negative 1 to 2. Negative 1 to 2, I changed the question a little bit. Is the function increasing, decreasing, changing direction, or does it have some kind of a local maximum there? So we've moved to this next interval. What's happening here? Well, we don't have the graph to answer this question directly about whether the function is increasing or decreasing, but we can look at the derivative. Pick, say, 0. That's in that interval. At 0, our derivative is negative 2, or 6 times 0 minus 2 times 0 plus 1. 6 times a negative times a positive is going to be negative, which tells us our function is decreasing. So we can get information. And it doesn't have a local maximum on the interval. It does have a local maximum right here, right at negative 1, because we're increasing level off and then we go to decreasing. So yes, there's a local maximum, but it is right at x equals negative 1. And this question about what happens between negative 1 and 2. But we're analyzing the derivative, and the sign of the derivative is telling us something about the function. All right, then what happens at 2? Well, at 2, let's see, the function has leveled off, so we're headed down, we level off. We don't yet know what's happening after, so we really need to look at, well, what's happening after. So let's look at the derivative, say, at 3. At 3, the derivative is 6 times 3 minus 2 times 3 plus 1. That's going to be positive, so the function is switched back to increasing, and so the fact that we go from decreasing to increasing means we do have a local minimum at x equals 2. So there is a local minimum, but it required a little bit more analysis before we really knew that, because we could have leveled off and kept going down. So we really have to look at each interval. But notice where the zeros are extremely important. But we now know something about this function. When we know the basic shape of this function, it's increasing, it levels off, it's decreasing, it levels off, and it's increasing. That's kind of the basic shape of the function. Now, we've been analyzing it, we've come up with a basic shape, but to actually graph this, we're going to need a little bit more. So, I've kind of been recording this on the number line. The derivative is positive, and so the function is increasing on the first part, and then the derivative switches to negative, so the function is decreasing on the second interval, and the third interval, the function's back, the derivative's back to positive, so the function's back to increasing. And then we decided, because of the increasing to decreasing, we had a local max at negative 1. And because of the leveling off and decreasing to increasing, we had a local minimum at 2. We know where those extreme values occur. We don't know what they are. So we need to now figure out, well, what's f of negative 1? Well, we've been looking at the derivative. Here we're going back to the function. F of -1, we go back to the function. It's 2 times -1 cubed minus 3 times -1 squared minus 12 times -1 plus 5. -2 minus 3 plus 12 plus 5, I believe is 12. So we actually can tell by going back to the function, and the value is 12. A number of people said 0. Most likely, you were still looking at the derivative. And yes, the derivative at -1 is 0. But we switch back to the function. So at -1, we've got this point, -1, 12. That we know is a peak. We are increasing, we level off there, then we go to decreasing. But now we know at what height do we level off. Up to this point, all we knew is where we level off, not how high we are. So we had to go back to the function to determine, okay, what is that height that we level out? So we knew there was a local max there, we just didn't know what the local maximum value was. We also decided at 2, we go from decreasing to increasing, so there's a local minimum value, but we don't yet know, well, what is that local minimum value? For that, we've got to figure out, well, what's f of 2? And so for f of 2, we go back to the function. So it's 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 5. Which, let's see, that's 16 minus 12 minus 24 plus 5. I believe it was minus 15, which was D, and a lot more people got D this time. So now we know we're over here at 2 minus 15, so we can make our graph even better than we had here, because we knew where the peak occurred, we just didn't know how high it was. Now we know, we can figure it out. We can figure out how low the valley is. We knew it occurred at x equals 2, because that's where we switched from decreasing to increasing. We just didn't know how low the valley was. So we found where it occurs first, and then how high or how low. And if we put it all together, we get a reasonable graph of the function. And notice, I only graphed 2 points. I didn't graph lots and lots and lots of points. Now you may say, well, I could have just put this in my graphing calculator. I don't have that up. Let me pull up the graphing calculator. And say, well, graph this function. 2x to the third minus 3x squared minus 12x plus 5. 12x. And actually, that minus isn't going to work. Doesn't like the keyboard entry very well at times. If I just graph it, don't see much of what I want to see. But now that I know the biggest height and the lowest valley and exactly where they occur, I can adjust my windows to kind of highlight those features. So knowing exactly where they are is helpful. So we could change our window and maybe go from -5 to 5, and maybe -20 to 20 in steps of 5. Once we know where the information is, we can kind of decide, well, what's a reasonable scale to actually show this? And we could, either by tracing along here, discover that yes, there is the peak at -1 with a height of 12. And over here is the valley with a depth of -15 occurring at 2. It's not exactly on the trace. There is a way with the calculate menu here as well to calculate where the min is. We've got to help it out a little bit and kind of give it an interval where we think the min is and kind of a guess for the minimum. It will do some work and tell us its approximation of the minimum. And notice it says the minimum's at 2.0000007, -15. It doesn't say 2. It's doing an approximation. So we can do it exactly and use that information to produce our graph and make those predictions. Now, suppose we only had a little bit of information. This little bit of information. G of 1 equals 3, G prime is 4, at 1, G of 2 is 6, G prime of 2 is 0, and G prime of 3 is negative. Even with that little bit of information, we can sketch a reasonable graph. When the input is 1, the output is 3, and we are headed up. By the time we get to 2, we're up to a height of 6, and we've leveled off. So this tells us what point, this tells us what direction. What point, what direction. This one doesn't tell us the point, but it does tell us by the time we're at 3, the derivative is negative, so we're headed down. So from the information we've got, that seems to be a reasonable graph that matches the limited information we have. And certainly there are times, we may like the full function, we may not have the full function. We just may, take a few measurements. At this point, what direction is the wind blowing? At this point, what's the direction of the wind blowing? What's happening over here? And use that to come up with an approximation for what the graph looks like. And so we can put together a reasonable graph. So, your assignment for next Tuesday are some problems from 2.7 and 2.8. We actually skipped section 2.6, and we're not actually going to come back to 2.6. We're pushing the exam back a day. 2.6 is what we're going to skip. So I will see you Tuesday. Yeah, I think I can get it figured out, but thank you. Yeah, because the others were not here, so I should be able to figure it out Which one is her?
Okay, mine turned off during the lesson, so I was clicking buttons
For a while and didn't realize nothing was probably happening?
Yeah, so if I went blank, it was probably because of that.
Okay, there are lots of people that are missing.
You have a good one.
Me too. So, 3 clickers,
Bye.
2 people.
Bye.
Okay.